will still under basic conditions and heat. So once again, our hydroxide can definitely add into the amide. Giving us something like this. And usually it's tempting to do a proton transfer, where this proton goes here, but does that make sense by pKa's? Absolutely not, right? Because an alcohol is going to have a pKa of 16, and an ammonium is going to have a pKa of about 10. So it just doesn't make sense for this proton transfer to happen here. But we're under basic conditions and heat, right? So one way you can think of it happening is real quickly it collapsing. To give us our product, but we're forming a really, really strong base in the process. Actually, let's have a teaching moment. I might go back, but I want to have the class vote on this. I don't do clickers because they don't work for this class, but I'll do by hands. So I'm going to give you guys two mechanisms I want to show of hands just to see what you guys like better. So first mechanism in blue is kicking up NH2 minus, giving us a carboxylic acid, the NH2 minus, which we quickly grab the proton, giving us the product. Or in red, we actually do the proton transfer I mentioned. To give us now ammonium as a leaving group. To give us the same product. So which one do you guys like better? Kicking up NH2 minus and a quick deprotonation? And so in this case, we're kicking something up the pKa of what, 35 or so? So this has the conjugate acid of this is a pKa of 35. And then this is a pKa of 16. So in this equilibrium, we're going from something with a pKa of 16 in the acetyl O minus to something with a pKa of 35 that quickly protonates itself in black. Versus in red, we have a proton transfer, so we go from something with a pKa of 16 to 9. So this deprotonation is going to be favored by 1 times 10 to the, going to be disfavored by about 6 orders of magnitude, roughly, right? 16 versus 10, ammonium versus alcohol. So this is disfavored by 10 to the minus 6. But this is disfavored probably by 10 to the minus 20. So which one of these routes do you think is more reasonable by your pKa argument? The proton transfer, right? I agree. So I take back my, oh, this proton transfer is tempting, and I'm going to say, there's a reason the proton transfer is tempting, because it makes more sense. Sean, you agree?
Yeah, I guess.
Anyway, this is just amide hydrolysis. Hydroxyl group's going to add, and then it's just going to be a amine kind of like the amine hydrolysis mechanism where I kick up, yes, NH3+.
Do you have a base pull off the proton on the OH?
So you mean do an intermolecular? Absolutely. Intermolecular transfers are always fine. So nitriles, again, are good electrophiles. You can make ketones, aldehydes, primary amines, depending on the conditions you use. You can also make carboxylic acid and carboxylates. So now, that's basically the key concepts of chapter 18. But since we just talked about nitriles, sorry, we talked about tautomerization in this mechanism. And just to redraw out the tautomerization, we have this intermediate. So we have this intermediate, and I tell you guys this intermediate was in equilibrium to this amide, be what we call a tautomerization. And the way a tautomerization occurs. So these two are, this is pretty much resonance structure of this, but just a proton moving, right? So with resonance structures, bonds don't break at the time. And thus with resonance structures, they're just contributors to an overall resonance hybrid. Tautomers are actually discrete compounds that are in equilibrium with each other. Tautomers are discrete compounds that are in equilibrium with each other, but they are somewhat related to resonance structures. And so one way to draw a tautomerization is to take one molecule, let's go here, let's draw a resonance structure. And so if we start from one neutral molecule and we draw the resonance structure this way, that's going to give us now a Zwitter ionic resonance structure. So most people would say this resonance structure is better than this resonance structure. But in a case like this, if we draw this resonance hybrid, we could draw a intramolecular proton transfer that now gives us this, where now the nitrogen with the minus charge takes a proton. And that gives us this compound. So these two compounds, which are called tautomers, are different compounds, but because they're so related via resonance, they can always be interconverting between the two. That's a very simple explanation of a tautomer. But we brought that up a couple of times throughout the lecture, like when we were talking about the carbodiamide mechanism kicking off urea. We talked about tautomerization there. I think I talked about tautomerization about 5 minutes ago. But I just wanted to show you guys another example of tautomerization, because now that we're starting with chapter 18, there's a whole lot of tautomerization in chapter 18. Yeah?
Does the environment impact?
Absolutely. Absolutely. In fact, I have seen drastic changes in tautomeric ratios by changing salt. So it's very important in the environment. It's also very important on the molecule itself. And I'll show you some examples shortly. But let me just tease what chapter 18 is going to deal with now. On chapter 18, we're still staying with carbonyls. But we're looking at carbonyls from a different perspective. Particularly in chapter 18, we're concerned about the hydrogens adjacent to carbonyls. So do you think there would be anything special about the hydrogens adjacent to carbonyls? Obviously, there's an entire chapter, several chapters actually dedicated to it in this book. Does anyone want to tell me right now what the special feature of hydrogens adjacent to carbonyls and what we call them is alpha hydrogens? Alpha hydrogens. Did someone say acidity? Yeah. So why are they acidic? Yeah. Why is an alpha So we take a base and we form the anion. So the fact that they're acidic means that the conjugate base is stabilized. So why is this stabilized?
The carbon has a partial positive charge next to that.
Yeah, that's right. I just like to think of it as resonance. Because you can draw a resonance structure.
Is that a baby H right there?
Right here,
Underneath the arrows, is that H right there?
this here,
Yeah.
alpha hydrogen.
Oh, oh.
So these hydrogens adjacent to carbonyls, we call them alpha hydrogens. So if the alpha as adjacent, if you had one more carbon removed, we call them beta carbons and so on and so forth. But adjacent, we call them alpha. So these alpha hydrogens are highly stabilized. I'm not going to draw the conjugate base, acid base. So because of this resonance, they're highly stabilized. And in fact, which of these resonance structures do you think is better? Minus charge in the carbon or minus charge in the oxygen? Minus charge in the oxygen. So because now the minus charge is being spread out from just the carbon over one bond, they're being over 3 bonds, with one of those bonds being very, 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 very electronegative, that's a huge stabilization event. So just to give you an example, what's the pKa of methane? About 50, thanks. Does anyone want to guess what the pKa of a typical alpha hydrogen is?
25.
About 20 to 25, depending on your situation. So the fact that we have this resonance stabilization with the carbonyl means that the conjugate base of a carbonyl with alpha hydrogen is 25 orders of magnitude more stabilized than if it weren't there at all. Huge stabilization, 25 orders of magnitude. So hydrogens adjacent to carbonyls are quite basic. Are quite acidic. What do you think the reactivity of a molecule like this will be? So a pKa of 25, would a molecule like this be a nucleophile or an electrophile? It's a nucleophile. When you deprotonate a alpha hydrogen from a carbonyl, you form a nucleophilic species. And pretty much the basis of chapters 18 is the formation of these, what we call enolates. The formation of these enolates and the reactivity towards electrophiles. Nothing really big changes. You take this, it's a nucleophile. Let me show you an example, let me draw an analogy real quickly while I'm thinking of it. What's the pKa of an alkyne with a hydrogen? About 25. pKa roughly 25. So in this class we talked a lot about using these deprotonated alkynes as nucleophiles to do SN2s or this or that, right? We've talked about, definitely in 232 as well, we talked about these deprotonated alkynes as nucleophiles. And they have a pKa of 25. These have pKa's of roughly 20, 25. So the nucleophilicity of a deprotonated carbonyl is not going to be that much different than a deprotonated nitrile. So really what chapter 18 is going to be dealing with is the reactions of these enolates with things like methyl iodide to do SN2, or reacting with electrophiles like I2 to give iodinated iodinated carbons out into carbonyls. So stuff that's not that different from what we've dealt with. And then you get into chapter 19 after that. Chapter 19, does anyone want to guess what the electrophiles in chapter 19 is? Other carbonyls. So pretty much the next 2 chapters, it's going to be nucleophile, electrophile chemistry. All we're doing is we're just changing our nucleophile to something we had previously thought as an electrophile. But of course, it's deprotonated, so it's